Hey class, so I told you that I'd make y'all a video for this unit, and so here I am making it. And basically what I'm going to do is just kind of give you a little bit of background information on waves, kind of touch base a little bit on the electromagnetic spectrum, but not really on the spectrum, but more of what electromagnetic waves are. And hopefully this will kind of help y'all on y'all's quizzes and on your tests, and you'll be kind of like, oh yeah, I remember that, because that's when my teacher was really weird in that video, and she told me about it. So hopefully this will kind of stick with y'all a little bit more than just watching some guy on YouTube that we don't even know who it is. So the first thing we're going to talk about is the Kola Super Deep Borehole. And probably none of y'all really know about this, but what it is a long time ago we tried, actually it was really in like the 1970s, so it wasn't that long ago, but y'all weren't even alive yet. I wasn't even alive yet. But basically what happened was in the 1970s, they decided to see how deep they could dig, because they were just as eager as we were to know, well, what does the inside of the earth look like? What's there? You know, how do we know? So they dug 40,000 feet, and then they had to stop. They could not dig anymore because it was so hot. It was so hot, and physically we just couldn't get any farther. So 40,000 feet. You're like, man, that's kind of far, you know, that's decently deep. Well, really, it wasn't that deep because we didn't even break past the crust. So we have the crust, we got the mantle, the outer core, and the inner core, and we couldn't even get past the first layer. So you may be wondering, okay, well, Miss Bunch, like, you told us that there's an inner core that's solid, and there's an outer core that's liquid, and then we have a mantle and the crust. Well, how do we know this if we only dug past, like, couldn't even get past the crust? Well, the answer is seismic waves. And these are how we measure how strong or how weak an earthquake was. And it kind of lets us know what kind of damages we're going to be dealing with, things like that. So what happened is seismic waves, and there's two types. There's a transverse wave in a seismic wave, and then there's a longitudinal wave in a seismic wave. Well, the problem with the transverse wave is that they have an oscillation that is perpendicular, and you know we normally represent perpendicular kind of like this. So they have an oscillation that's perpendicular to the motion of the wave, and so these waves couldn't make it through the solid inner core, and they can't make it through the liquid outer core. So we could only kind of know about the mantle and the crust with the transverse waves of a seismic wave. So then we decided to take the longitudinal part of a seismic wave. And these have an oscillation that is parallel, which is represented kind of like this. So they were parallel to the direction of the motion of the wave, and they were able to make it all the way into the inside of the earth. So that's how we found out that we have a solid inner core and we have a liquid outer core. And then we have the mantle and the crust. So that's kind of how we figured out how the earth is, a little bit about the two waves. So I'm going to explain a little bit more about those two types of waves. So waves are just ways to transfer energy through oscillations or disturbances, and they come in two forms, which is longitudinal and transverse. Longitudinal waves are the ones in which the oscillation is parallel to the propagation or the movement of the wave itself. In transverse waves, the motion is left to right, but the oscillation is perpendicular to the wave. So a way to think about this is you got longitudinal and you got parallel. Well, longitudinal has L, parallel has L's, so longitudinal goes with parallel. And then you can think transverse is perpendicular, and perpendicular is kind of represented with like a little bit of a T. So you can think transverse and perpendicular together, so you can keep those two straight. Maybe that'll work, maybe it won't. I don't know. We'll try. But anyways, so a transverse has an oscillation that's perpendicular to the wave. So they're still going left to right, but they're perpendicular. All of these waves are examples of mechanical waves, which require a medium to go through them. An example of a wave that does not require a medium to go through is an electromagnetic wave, which is a type of transverse wave. So not all transverse waves require a medium, because we have the electromagnetic waves, which are transverse waves, which do not require a medium. An example of an electromagnetic wave is the light that we see right now. That's a type of electromagnetic wave, because right now it's requiring all it's going through is the air. So that's how that works. Another thing that's kind of neat is a lot of you may have like Ray-Bans or Oakleys or Under Armour sunglasses, whatever kind of sunglasses you got. You may have polarized lenses. They cost a little bit more, but they're totally worth it. And what polarized lenses do is they have thin slits in them that only allow certain transverse waves to get through. So you're not having those painful rays hit your eyes. It's just the rays that you need to see so that you see light at all. So that's kind of how polarized lenses work. But anyways, so that's all I've got for today, and I hope you take notes and that you study for your quiz, because you're going to have one.